Hey, hello again. I just thought I'd do a video here on the Don Smith. I've been working on Don Smith for a while, and that's kind of carried over to the cool Ruslan, stuff. But there's we know Don Smith's based a lot of his stuff on Nikola Tesla, obviously, and so I just wanted to kind of show you guys what I've been doing to kind of look at what Don had done and try to look at his drawings, figuring out what frequencies he was actually running this at, because in the videos and lectures and stuff that he's done, it's not very clear, and you can actually work it out pretty simply by just looking at the capacitors here and here, and we know the core that he has, well, the coil, sorry, he has. If you go on to the website, Barker and Williamson, they sell these air ducts coils, and you can't buy them. I got this one, and this one here, no problem. That was a couple of years ago, but it says here now they don't sell to individuals, so I guess you got to try and buy it through some kind of supplier. But anyway, it looks like if you're looking at Don's coil, I think that his is the T404TL. Okay, it's 32. The inductance is 32 microhenries. The coil length is 10 inches. When they say coil length, it's from here to here. It's that length. It's not the actual length of the wire. It's a 3-inch coil, and it's 4 turns per inch. Wire size is 10. So I didn't get that one. I thought it was like a 2.5-inch coil. So I got this one, which is the T004, sorry, 2004TL, 22.5 microhenries. It's a 2.5 inch diameter, 4 turns per inch. Wire size is 12. So it's a little bit different than Don's. So you can see the inductance is different. So, but if we know I think this is a 3-inch coil, because the next one up is 4. It's possible that's 4 inches. God, I don't think so, but I guess you could do the same math and figure it out if it was. But I've kind of gone through some of the numbers, and Don's coil, assuming it's the 2404TL, and the inductance is 32 microhenries. The length of wire is about 9.6 meters. Quarter wavelength of that is 9.8 megahertz. Okay. So, and we can see on Don's coil, it's a 0.04 microfarad cap on half the coil. So you remember, it's on half. It's not the whole coil. So you have to figure out what that's resonating at. You need to just take the value of that capacitor and then half the inductance of the coil. All right. So we know the inductance of that coil, assuming we have the coil correct, it's not a 4-inch, it's 16 microhenries. Okay, and then the cap is 0.047 microfarad. That would give us 183.5 kilohertz. So he was resonating this at 185 kilohertz, basically. The L1, you've got to kind of have a bit of a guess on this, because we don't know the actual inductance of what his L1 was, but I know what mine is, and it's pretty similar. So we kind of make a guess, really, if we're running around 183 kilohertz, I kind of figure that his is probably, go back over here first. This cap is I think it's 2 caps, and they're both 0.1 of a microfarad, so that's 0.2 of a microfarad, I believe, on those. Can't really see on this, but so if you work that out, and just say his is 3.6 microhenries with a 0.2 microfarad cap. That would give you resonance frequency 187.5. Now this is a bit of a guess, but I don't see how this is a guess because, well, unless the coil's wrong, but you still, the next coil up would be 57 microhenries, and so half of that, okay, with this capacitor will give you that frequency of what this was running at. But the point I'm trying to make is, if you look at this and you work backwards from what you can see, you can kind of see what frequency this is running at, and the what it looks like to me is he matched obviously the frequency of the L1 with the frequency of the L2 perfectly. All right, and so I just wanted to go over that, and how you go about doing that. You know, he has all of this, you know, this is just like a little variac. That's a 12 volt, 12 to, I think, 110 volt or something power supply. I can't remember what it is, but that feeds like a neon transformer. You don't need to do all this necessarily. You can just get a, you know, a MOT, a microwave oven transformer, and it, you know, it doesn't even matter the frequency you're putting into this, because this frequency is really irrelevant. Okay, the variac, we know this is running off 60 hertz, but the 60 hertz going into this, it doesn't. It's irrelevant to what's going to happen further down in the circuit, because we're going to be depending on how wide the spark gap is, how much voltage you're pushing through this thing, and then your LC circuit for your L1. That's what is determining the frequency of what this L1 is going to resonate at, not what you're putting into it. Okay, so you know, right now I've got this pretty well tuned to, I think it's 185 kilohertz, and if I flick and the nice thing about this is a 2000 watt transformer, right? So that's at 120 volts. Outputs 2000 volts. So at 60 volts we should have about 1000 volts out. I'm inputting about 35 volts into this, so I'm only getting out around 800 volts or so, roughly. My meter only goes up to 600, so I can't measure it. But it's, you know, assuming this, you know, if you're looking at what you put it in and what we should get out, I can get this to spark over at a fairly, you know, you basically want to get that sparking as low a voltage as you can. You don't want the voltage to go too crazy, so you can handle it down the line. So, you know, if I flick this on, I get a little spark gap there. You know, I've just got a little bulb in there, it's not drawing a lot of current. But that, with that bulb in there, it's about 180 volts DC on this cap with 29 microfarad cap. If I turn it up a little bit, you know, put 40 volts in, the light gets brighter, voltage is going up, right? But this is just one part of the circuit, right? For Don Smith, I mean, I'm right now, as I'm taking the load right off this cap, but they say not to do that. I mean, if you look at his Don stuff, it's you know, you're creating your huge magnetic field, right? And we're getting that voltage into the caps, all right? But this is just a gain. This is like an amplifier. This is gaining your voltage. They don't have the next piece of this. The next piece of this would be the step down transformer, and that's not in here. So I'm not exactly sure how that has to be set up. I would assume it's some kind of resonant step down transformer, which I haven't got to that point yet. So I'm just working on this bit of the circuit. So that's why I'm just going to show you guys what I think is supposed to be going on with this piece. So so Don's is, you know, Don's you can work out just by, you can see, if you can find this stuff, these photos of Don stuff online. And I'll tell you, a good book to get is Richard Friedrich. He's done this book. He's kind of catalogued all of Don's writings, which is really, really helpful actually. I mean, I had most of this stuff, but now it's in one book. It's just It's a really great book, and you've got a lot of stuff that Don's said in different forums and whatnot. So I recommend getting that. The other good book to have is this book from Tesla. I guess Thomas Martin wrote it, but there's some excellent stuff in here. Probably page 219 is probably one of the most important passages, I think. If you can understand these couple of pages here, you'll probably kind of get what's going on. I'm having a lot of trouble. That's why I keep reading it and underlining it and reading it over and over and over. But it's pretty good. The other thing about this is that if the drawings in here, it kind of this is basically the Don Smith drawing, right? What we're doing here. I mean, this is what we have going on. This is what I have going on right now. Is this circuit? Okay. I don't have this part. I don't have the step down transformer. Sorry, this is the one we're using. I don't have this part. So, but this is Tesla. So this is all Don was copying, and so I recommend you read from the horse's mouth. But what I've done with mine, I actually, I really wanted to get it exact, so I unwound the wire off this thing. You can get it off and on. It doesn't go back on very nicely though, unfortunately. And I measured the length, the length of the wire, and my total length was 8.08 meters. Okay, quarter wavelength of that is 9.27 megahertz. All right, so that's a quarter wavelength. So you want to tune to a harmonic of that frequency. Okay, so you want to have the wavelength frequency. So you have longitudinal and transverse frequency, right? I think when they say inductance resonance inside and resonance, it's longitudinal resonance and transverse resonance superimposed upon one another. I mean, that's the way I read it. I could be wrong, so the wavelength frequency, okay, you need to tune to a harmonic of that, and the 50th harmonic of 9.276 megahertz is 185.5 kilohertz. Okay. The important things to understand too when you're tuning this stuff is, let's just turn this off. If you look at the inductance of the L1, it's important to understand that when you have an LCR meter, there's all different types, right? I mean, this is a fairly decent one, but this one you can actually change the frequency on, right? So here, right now I've got it set at 0.8 kilohertz, so it's 800 hertz. And if I want to test the inductance of this coil, the L1 coil, okay, which is that there, L1, you can see here it's 17 microhenries, the inductance. That's at 800 hertz. Now, if I increase the frequency on this, okay, that's 15 kilohertz. I know that I want to tune this around 185, so I'm just going to go, this particular meter only goes up to 200 kilohertz. So now at 200 kilohertz, it's saying that I have an inductance of 1 microhenry, which is strange because I should have like 2.5. Yeah, we go. Right now we're saying 1.9 microhenries of inductance, okay, at 200 kilohertz. And I guess the point I was just trying to make, if you change the frequency right down to 15 kilohertz, and let's go into at 1 kilohertz. At 1 kilohertz, I got 12.5 microhenries, okay? But if I go up to into the kilohertz range that I want to use, which is around 200, it's dropping down to 1.9 microhenries, which is interesting because that's the lowest I've seen. Last time I tested this, it was like 2.5 or something. But the point is, you need a good inductance meter that you can change the frequency on, because essentially this is going to help you, figure out what size capacitor that you need to use. These are rather big capacitors, oil filled, and this is just a obviously not oil filled, that one, but I had to add these together to get the value that I needed to get my L1 resonating at 185 kilohertz. So, and then I guess the easiest way to see what you're resonating at is, put this together. You need to close your spark gap. I always like to have everything kind of together how it is when you're going to be running it, if you can, because then it's it's going to give you more of an accurate reading. So because I want to find out what L1 is, this resonant frequency L1, I'm going to use the L2 coil I'm going to put a frequency on that to induce the frequency on the L1. So all I need to do is let's just do half the coil. Okay, we're going to input a signal on this half. All right. And I've taken that capacitor out because I just don't want this in that circuit. I don't think it will affect if I left it in there, but here's my frequency meter. So right now it's at 185. Okay, I need to put oscilloscope on here. See what we got going on. Alright, so this circuit now, I'm just going to read when I get a rise in frequency, or the peak. I want to see what the peak is when I put frequency here on the L2. So you can see right now I have 187 kilohertz going in. This is a square pulse, and I have a fairly decent peak. And if I take the frequency down, okay, that's down to 160 kilohertz. It's dropping down. Go back up. All right, here we go. That's about the peak right there at 185. So right at 185 is kind of where I'm getting my peak. So that tells me that this inductor with these capacitors is going to resonate at that frequency, regardless of what frequency I'm putting into this circuit. This has nothing to do with what this side of the circuit is going to resonate at. Okay, this is just giving you the high voltage that you need, okay, to get a spark to jump across there. All right, and then the next thing we would want to do is test our resonant frequency of this and this cap. So you just reverse it. Okay, what we need to do, can we put the cap back in? Okay, you can see getting this to resonate perfectly took a lot of work to get the right capacitors put together, so I don't have a lot of caps. Okay, all right, and now now I need to put the oscilloscope on this side. I can just get this done for you. That's the center. Right, now we're going to see what we got on that. So I need to put a signal in though. All you have to do is undo one of these. Okay, and I'm just going to go, right now we've got 177 kilohertz, alright, coming into this L1 coil, and we've got the oscilloscope on the L2 coil, alright, on this LC circuit. We're going to see what it's resonating at. So it's at 177 kilohertz right now. Let's wind it up. Okay, it's coming up. You can see it's getting to a resonant point. Alright, so let's get you a nice signal. So let's see, we got a peak right there. Okay, and look at that. It's 185. Right at 185 kilohertz is our peak. All right. So now I've tuned the L1, okay, to the L2. I mean, that was fast on the video. It took me forever to get the right capacitor set up to make that resonate. But that is, I think, how you're supposed to go about it, and it's all about making sure that you're tuning this to a harmonic of the wavelength frequency of the coil, if that makes sense. Hopefully I've explained it. And this is really just to get your voltage, and this is like your amplifier. This is the way I think about it. And to get your voltage up and get your a lot of energy stored in your cap. And this isn't just going to put out the energy at over unity. You still have to step it down, and the stepping down process, I think, is the critical part to getting the over unity out of this device. So that'll be in the next video. All right, thanks.